Good afternoon and welcome to the Embedded Executive Podcast. My name is Rich Ness. I am with Embedded Computing Design. This week's guest is Mark Saraghetti, and he is the Vice President of Product Line Management for Synopsys. How you doing, Mark?
Great, Richard. Good to be with you.
Thank you very much. So I want to get right into this because this is a pretty complex topic, one that I'll admit right off the bat, I'm not an expert in. So I'm going to lean on you to help me figure this out. And the topic of the day is digital twins. I know this is becoming a more common practice because designs are getting more complex. So I'm going to just stop right there before I say something that doesn't make any sense at all. What's the purpose behind the digital twinning, and why is it necessary with more complex designs? It just seems to me like we're actually adding an additional layer of complexity, but you're going to tell me that that's actually the opposite, right?
Exactly. Yeah, so I mean, look, the word digital twin is an interesting word because it's being used in a lot of different contexts, right? And ultimately, if you go to the base definition, a digital twin is a virtual representation of a physical product or a process or that is used to basically enhance what a company, engineers in a company, maybe people doing operation in a company are trying to achieve. So to me, when we talk about digital twin, what's really important to understand is what is it you're trying to do with that digital twin? Because then you can go and say, okay, what is my digital twin about? So for us, for example, here, probably today we'll talk more about electronics digital twin, right? Because that is the area of interest. We'll talk about other digital twin because they connect, but let me start maybe more with the electronics digital twin. And the way we look at it is if you're in the world of physical AI, and actually other world as well, but physical AI is a really important area. There's more and more electronics, there's more and more software, hardware in those devices, right? There's this trend towards we want to be software-defined product, and AI come in all this. So the content of electronics is growing. And if you look at the challenge that companies are being faced with is a traditional development means at some point you get to a physical test bench, and you start using that physical test bench for testing. But that's really late in the process. And you're faced with the issue of cost, quality, time to market, innovation. And nowadays, everything you can do to help you accelerate your development, start earlier, improve your quality is important. And that's really where the digital twin comes in the picture here. And in particular, in our case here, because there's more electronics, hardware, software, you need to be able to address that part of the development as well.
So if I understand what you're saying, it doesn't matter if it's hardware or software, but you're making a virtual digital twin, even if it's hardware, right?
Yes, exactly. So today, and I'm going to take a lot of example in automotive because that's a market we are all very, in general, familiar with. We all drive a car. But today, what's happening? Today, the companies that are doing this are trying to verify, validate what we call electronic control unit. And for this, they have a physical test bench. That physical test bench requires the physical hardware to be available. And it's very complex. It's like basically, it's almost a big bang integration. So what can you do to really solve the issue of a big bang? Well, if you do things earlier, if you have alternative to the hardware being available, then you can really start shifting left. You can solve a problem earlier. Ultimately, that's all what it is about, right? Make sure that you can do things earlier such that as you advance, you focus on the more complex problem that can only be identified once the hardware and the full system is available.
But how do you guarantee that your twin is actually an exact replica of the physical hardware?
So there's multiple components. A very good question, because ultimately it's still a virtual representation. So this is where it goes back. What is it you're trying to verify? What are the capabilities the twin offers to you in order to achieve what you're trying to verify? And ultimately, if you look at an automotive system, you may be trying to functionally validate that the software is running, that it has the right behavior. That is very different than if you're trying to validate the exact timing performance of all the software. So again, the key here is not to say that you are eliminating the physical test bench. The key here, you are shifting left because there's a lot of issues or problems you can address and fix well before you get to an expensive, hard to maintain physical test bench. Today, I've talked to quite a bit of OEM companies, and what they are saying is we get to those physical test bench, the engineers, that's the feedback from the engineers. They say we get to the physical test bench and, I find all sorts of problems that, we should have found earlier. So this is a very important part. How do you do things earlier, and how do you avoid big bang integrations?
Why does this sound very similar to what we used to call emulation?
Well, emulation is a form of doing that, right? So again, it goes back to the use case. You can do this with virtual, you can do this with emulation. So you can do this with FPGA prototyping. Each of those different engine, let me call them engine, provides different capabilities. And some are relevant to specific use case. So if you take emulation and you're looking at validating the performance of your SoCs, your performance of the power, that's the right platform to do this. If you're a software developer, you're trying to validate the functional behavior of your software, and you have a larger software team, you need something that you can deploy easily to a large team of engineers, something that's fast. And that's where virtual now comes into play, because virtual, you can also do it before even things like RTL are available on emulation. The other thing maybe to add to this is, in the world of physical AI, really, if you think software is starting to have a very different life cycle you need to manage. In general, you take a car, you take a plane, an industrial device, you build it, you physically build it, and then you put it in the field. But nowadays, if you think software plays an increasingly dominant role with the hardware supporting it. But software never stops. Software continues to be validated. That's why you have all those concepts of over-the-air update and things like this. So that's really a different life cycle you have to adapt with, and a continuous life cycle, basically, because software is validated, continuously validated and updated on those new devices.
I think where my confusion came in, what you're describing is that there's not one size fits all. Depending on what your end goal is, there's a different way to produce your digital twin. Is that accurate?
Absolutely accurate, right? Somebody that's doing application software may need an abstraction that is in the software itself, in the lower level of the software. Somebody that's looking at hardware-dependent software may want a virtual model of the hardware. Actually, there are definitions that are being used in the industry, in automotive, for example, for what we call the virtual ECUs. It goes from level 0 through level 4. These represent different level of abstraction of virtual ECU, and they will serve different purpose. Level 4 tends to be what we would represent as a virtual hardware, meaning you can validate the hardware-dependent software and the full software stack. Level 1, 2, 3 abstract more at the software level for people maybe doing application, people doing middleware, or people doing operating system type of activity. So this is a very important point here that I think it's important for the audience to understand is as you go in the world of digital twin, there's multiple aspects to consider. Number one is, what problem am I trying to solve? Once you understand which problem you are trying to solve, the question is, what type of digital twin do I need to build for that? And that has implication on methodology that an executive may have to deploy in a company. This may have impact on organization as well. How and which team need to be involved in order to get the benefit of those digital twins.
So can I just go out to my AI engine of choice and say, build me a digital twin of XYZ?
So AI is an interesting topic, right? Because AI will touch every part of a digital twin. You can think of in digital twinning, you're building model. How can I use AI to build those models? It's a very natural way to think about it. Another area is, ultimately what company want to do is, how do I make my verification, my validation more efficient? Well, you could think about AI playing a role in this. Is like, I made modification XYZ. What does that imply in terms of what do I need to test? I don't want to brute force and continue testing all across the board. Another example would be, we're talking systems that are complex, that have physical elements, maybe live in an environment, and you're observing a problem. But what is the root cause of that problem? Could be in a completely different place in the system. How can AI help on that side? And of course, this is verification and validation. So, you can think of concept like agentic AI that will play a role in managing that overall process, being more efficient there. So I think AI is an underlying key element of an electronic digital twin. And if you look at it, you have to think beyond just electronic digital twin. You have to think about a platform. And this is really a change of mindset from, oh, I'm just creating and using an electronic digital twin, from I'm building it and now I'm managing its deployment. So let me maybe relate to something, try to give an example of why this concept of platform becomes important. So the first example I will use is, I was talking to an OEM, and they say, well, Mark, in the past, we would go to a tier one and we would say, build me an HVAC air conditioning system for the car. They would say, okay, here is a box, some software runs on it, some CAN interface integrated. And nowadays we go to that same tier one and say, well, give me an air conditioning system, but give it to me in software. And that software will be integrated into maybe my central compute, or will be integrated to run on different zonal controller and things like this. And so the first reaction of the tier one is, well, how do I go and test this? Because now I'm not in isolation. And I think that's a very important aspect of what's changing as well in the market. It's not just, a traditional sequential hardware-based development. It's a collaborative software development. So the electronic digital twin itself can help and can be that, representation on which you help that collaboration. But the second part is you also need to be able to deploy it. And that's where the cloud play an important aspect, because the ability to share environment, to enable people to collaborate, become important. So that's another element I wanted to highlight here as well, how that development is changing from sequential to collaborative, and the electronic digital twin and the platform basically enables that collaboration.
We started off by saying how simple this is going to make our lives, but man, sure don't sound simple to me.
Well, the idea is to make it simple. The reality is what's becoming more complex is how those systems are developed, right? How they are themselves are becoming more complex. I mean, people don't look at doing software-defined product just because, well, I need to do software-defined. It's because there's a business opportunity to it to provide more services. There is a customer relationship aspect about providing over-the-air updates. So those are the capabilities that are really driving what company needs to do. And for this, that means it's affecting the architecture, the hardware architecture of their product. It's affecting the software content, the amount of software in this. So all what we're trying to do here is provide them a platform that really enables them to achieve those goals of really and truly getting the benefit of software-defined products. So yes, it is more complicated. It provides a bigger return. And for this, you need to put in place the tooling, the methodologies, the organization that enables you to get there. It's almost a digital transformation that people have to do in order to achieve this transformation.
And what's the role that Synopsys plays here?
So I think Synopsys plays a key role in terms of we provide the infrastructure that enables company to create, deploy, and use those electronic digital twins. And there are multiple elements to this. There are one element, which is obviously technologies. We do provide a stack of technologies that is part of our platform, starting from simulation, emulation capabilities, the models that you need to have, the ability to build and assemble more complex systems. So just an example on that side, when we talk about cars, car is made of multiple ECU. They need to be integrated with each other. So you need to have an infrastructure that enables you to build that electronic digital twin, which is made of multiple control units. This is, for example, where we are collaborating with Vector around an infrastructure called Silkit. You need the tools to enable you to actually use that electronic digital twin. You need the tools to deploy it. So the first thing that really Synopsys does is bring this infrastructure. The second part is that I think is important is the ecosystem. Does Synopsys bring every capabilities, every simulation, every tooling? No, actually no company does this. So this is where having an open platform is a very key element. And you need to have connection and integration with ecosystem companies to deliver that electronic digital twin. And that's a very important aspect because the breadth of what you need to provide is pretty large. If you look at some of the things we are doing, we're working with semiconductor to provide virtual models of their SoC, of their microcontroller. We are working with the software ecosystem to make sure that operating systems, software, middleware is integrated in a virtual hardware or in a virtual ECU. We're working with tools that are simulating other part of the systems. So when, at the beginning, we talked a little bit about digital twin, different type of digital twin. Well, in the world of physical AI, you have the electronic digital twin, which we provide, but you will need physical digital twin because those are physical elements. And Synopsys obviously plays in that space with our NSYS acquisition here and the technology they bring in, but there's a wide variety of tools there as well. The other thing is when we talk about physical AI, it's a it's a product that has mechanical element, that has electronics, but lives and moves in an environment. So that means you will need an environment digital twin, something that sense and the environment. So this is where also we bringing ecosystem partner. So an example in this area is IPG Automotive, where we are working together to connect an electronic digital twin with the environment digital twin. And then on top of that, you have an entire ecosystem of company that, like system integrator, that work with the OEMs in automotive or system companies to bring this into their environment. And then the cloud provider are in this area as well. So this is a key element that Synopsys bring, which is working and bringing together that ecosystem such that into an open environment, such that companies that want to deploy those electronic digital twin don't have to focus on building the pieces together, but rely on pre-integrated technology, rely on expertise that has been shared between suppliers such that it can be easier for them to deploy that and they can focus again on their use cases.
Very good. Well, thank you very much. I think I understand it now.
Great. Thank you.
That was Mark Serighetti. He is the Vice President of Product Line Management for Synopsys, and I am Rich Nass with Embedded Computing Design. Thank you very much, Mark. I appreciate your time.
Thank you, Rich.